All right, in this video, we're going to go over section 8.3, solids of revolution, but this time it's the washer method. So one of the things that I want us to recall is the disk cross sections that we learned from the last section. So remember how I said, like, if we were to slice any of our volumetric shapes, like through any point, and we kind of looked at the cross section, it did sort of look like a solid disk. That's why we call it the disk method. All right. In this section, though, what we're going to notice is that if we were to go ahead and slice at any point in the and look at a cross section, you're going to notice that there's going to be a hollow space in the middle. And really, the area or the volume that we're interested in figuring out is that volume around the edges like that. Okay, so there's going to be a hollow space whenever we do these volumes, and this is why we call it the washer method. Because if you look at it, I mean, I don't know if you guys ever built anything, but that's what a washer looks like. So the formula is very simple. You have the volume is equal to pi from A to B, similar like to before, of the outer radius squared. But what you're going to do this time is you're going to have the outer radius like that. This is what we call Rx. And then in order to figure out just the area or the volume of this region right there, you have to subtract whatever the inner radius, which we're going to use, call it r, little rx. So we're going to subtract that from little r of x squared dx. Okay, and that's it. So as long as you can figure out what the outer radius is and what the inner radius is, and sometimes that's going to be the tricky part, is knowing whether or not you add a number or a constant or something like that. But once you get the right setup going, you're pretty much good to go. All right, so let's just kind of see an example of what this is like. So they're saying, find the volume of the region enclosed by y equals square root of x, that's this one, right, square root of x, and y equals x squared, which is that one right there, is rotated about the x-axis. So this is how we're going to rotate it. So it's kind of like what I did before. I'm just going to show you guys, like, the visual by drawing a mirror image of the figure, right? And then you'll notice that, and I wish I had some technology to kind of show you guys, just sort of what this looks like. But if you rotated this figure all throughout, you're going to end up with a nice hollow space, like within that region right there. And if I were to slice this at any point, it'll look like pretty much a washer. So the main thing that you got to do here is you got to figure out, okay, well, first of all, what is my outer radius? So I'm going to say r sub x, or not sub, r of x. So my outer radius, if I think about it, if I'm rotating around this x-axis, my outer radius is going to be pretty much whatever square root of x is. And then my inner radius, little r of x, is going to be from here to my inner radius. Because if I think about it, if I were to draw like these circles, that outer radius corresponds to the function square root of x, and my inner radius corresponds to x squared. Okay, so if I set up my integral as such, it'll be pi, so volume is equal to pi from, let's see, it's from 0 to 1, that's where they intersect. So from 0 to 1 of the square root of x squared minus the inner radius, x squared dx. Okay, then of course I can simplify this a little bit more. So that's pi from 0 to 1 of x minus x to the fourth dx. All right, and I trust you guys to do the integration, so that way I don't make this video longer than I wanted to, and I always seem to do that, but whatever. All right, so now let's look at this one. I'm pretty much using the same two functions where I have the square root of x right here and x squared right there, but this time I want it to be rotated around the line y equals 1. So this line right here is going to be how I want to rotate it. Okay, so if you notice, I can go ahead and draw my mirror image kind of like that, right? And then you'll see that, okay, well, I have my, like a revolution around y equals 1. Okay, this one's a lot different, and I'll let me explain why. So, because the trick is knowing what the radiuses are. Okay, first of all, when you think about the square root of x, or what that, the radius, or like from before, where the radius square root of x and x squared, that's the distance away from the x-axis. That's just how it always works whenever you're thinking of a function, right? It's always with respect, or like the distance is with respect to the x-axis. But this time, it's with respect to this line up here. Okay, so now I got to think about, okay, well, my outer radius is this distance right there. Let me zoom in on that. So this is my outer radius, okay? And if you think about it, well, my outer radius is going to be, let's see, it kind of corresponds to the x squared function, right? But the thing is, if I use my x squared function as my outer radius, well, that's telling me what this whole distance is from here to there, from the x-axis to that function, okay? But that's not the distance that we're interested in. We're interested in the distance above that. So really, if you think about it, you know that the entire distance from here to there, or from here to that axis of revolution, is 1, right? So we know that this is 1. This little distance is represented by x squared. So if I want to know what the other part of the distance is, I have to get 1 minus that little portion, and that gives me the radius that I'm interested in. So it's 1 minus x squared as my outer radius. All right, so let that sink in. If that doesn't make sense, rewind the video, or maybe ask me a question about it later, because that is extremely important, and that's the part that most people would mess up, is deciding what the outer radius is. All right, the outer radius is this distance right there. If we know that this smaller distance, or not always smaller distance, but if that distance below it is x squared, but the whole distance is 1, to get that piece of it, it's 1 minus x squared to get that. All right, and we're going to do something pretty similar for the inner radius. So this is the inner radius right there. That's what we're interested in. I wish I had a different color. I have black, whatever. So I know that this distance right there is my inner radius, and that's represented by 1 minus whatever that distance is. So that's the square root of x. So 1 minus the square root of x would give me that radius right there. So it would be 1 minus the square root of x. All right. I'll tell you right now, that's probably the toughest part for kids to wrap their heads around. But with enough practice, you'll hopefully get the hang of it. So now we can go ahead and use our volume formula. It's not that difficult. It's just pi times the integral from, again, 0 to 1. Same bounds as before. From 0 to 1 of my outer radius, so 1 minus x squared, minus my inner radius, which we said was 1 minus the square root of x squared dx. And there you go. I would go ahead and just multiply this all out. So that's pi from 0 to 1. That turns out to be 1 minus 2x squared plus x to the 4th. Sorry, I don't know if you guys can hear that, but my laundry machine's going crazy. All right, minus, then if I multiplied this out, that would be 1 minus 2 square root of x plus x dx. And I guess I'll take it a step further and combine my like terms. The ones cancel. It's 1 minus 1. Negative 2x squared can't be combined with anything else. I'll just write it there. X to the 4th can't be combined with anything else. I'll leave that there. The negative 2 square root of x would be plus 2 square root of x. And then that'll just end up being minus x dx, right? So from here, you can just go ahead and take the integral, and this is an easy integral. You just have to use the power rule, add 1 divided by whatever that is. All right. So again, for this video, I'm mostly just focusing on making sure you understand the setup of these volumes of revolutions, because at this point, once you should be good with the integration at this point. So let's see where my other page is at. There we go. So if I look at the next 2 examples, just 2 more examples, I don't think I need to go over a million examples for this. I just need to show you if a couple of examples of like each type of scenario you would see. So with these 2 examples, what we're going to do is we're going to rotate it about a vertical line. All right, so with this one, it says find the volume if the region enclosed by y equals x squared, so this is the x squared, and y equals 2x minus 1, so 2x plus 1, sorry. is rotated about the y-axis. So here we have the y-axis, and this is how we are going to rotate it. So the thing is, if we want to know what is the distance from the y-axis to each of these functions, we would need to write these functions, well, not necessarily functions, but we would have to write them in terms of y, right? So get x by itself and then write everything else after that in terms of y. So that's what we're going to do. So this x squared plus 1 function, I'm going to rearrange that around to get x by itself. So let's see. So if I get y equals x squared plus 1, I'll subtract 1 and then square root it. So x is equal to y minus 1 square rooted. And then for the y equals 2x plus 1, I'll subtract 1. I probably could have picked a better number, but whatever. I'll subtract. Sorry about that. I got interrupted by a phone call. But okay. So yeah, we need to get x by itself and then in terms of y. So I'm going to go ahead and move the 1 divided by 2. So that'll be x is equal to 1/2 x minus, is it minus? Yeah, minus 1/2. There you go. All right. So those are my two functions. If I'm, and that's the thing. If you're rotating about a vertical line, make sure that your functions are in terms of x equals, or your equations are x equals. So, okay, now I got to figure out, okay, what is my outer radius? My outer radius, because if I'm rotating this about the y-axis, it's going to be kind of looking like that. Horrible. Yeah. There we go. Yeah. So revolutions around there. So my outer radius is going to be that the quadratic or the square root. So it's going to be square root of y minus 1. And then my inner radius is going to be the other equation. So 1/2 x. No, I meant to say y. And why am I saying rx? It's ry. Everything's in terms of y. Come on. My bad. So that'll be 1/2 y. God, this is sloppy, but whatever. I think you get the point. 1/2 y minus 1/2. Okay? And now we're just going to go ahead and set up our integral. So the integral is going to be from, it looks like it's crossing at 1 and 5, right? Y values of 1 and 5. Pi goes on the outside. And then my outer radius squared is going to be the square root of y minus 1 squared minus my inner radius, 1/2 y minus 1/2 squared dy. Okay? And then I'll let you guys take care of that. Well, I'll at least do the next step. So it'll be pi from 1 to 5. That's squared, we'll just get rid of the square root of y minus 1 minus, if I had to FOIL that, well, first term is 1/4 y squared. Let's see, minus 1/4 y minus 1/4 y is minus 1/2 y plus 1/4 dy. Okay. And I guess I'll just take it a step further. So that'll be pi from 1 to 5. What can I combine here? I can combine the y's, right? So if I combine the y's, that'll be y minus negative 1/2. So that'll be like y plus 1/2 y, which is 3/2 y. The negative 1 can combine with the 1/4. So negative 4 over 4 minus 1 over 4 is minus 5 over 4. And then I have minus 1/4 y squared. It's not in the order, the like highest degree to lowest degree, but whatever, you'll get the same answer. All right. So I'll leave you guys to that. And so the final example that I want to go over is this one, where you'll notice same two functions, right? So if I'll just rewrite it for you guys here. X is equal to the square root of y minus 1, and x is equal to 1/2 y minus 1/2. Okay, but this time they want you to rotate about the line x equals negative 1. So this time you're going to rotate it around this vertical line. Okay, so it'll look kind of familiar to what we did before, where we added a little bit more to our radius. So if we want to think about what is the outer radius, well, the outer radius is going to be that inverse quadratic function. So not inverse quadratic, but you know what I mean, like the square root function. So it's going to be the outer radius is the square root of y minus 1. And then, but we have to augment this right there, right? This extra space of 1 has to be added to the radius, okay? And the same thing with our inner radius, right? So from here to our inner radius is going to be whatever that equation is. So 1/2 y minus 1/2 plus 1. I'll just write it, whatever. Minus 1/2 plus 1 is the same thing as 1/2 y plus 1/2. Okay? And that's about it. I'm just going to go ahead and set up my integral. So pi from, same thing, 1 to 5 of square root of y minus 1 plus 1, all of that squared, minus 1/2 y plus 1/2 squared dy. All right? And like I said, I'm going to trust you guys to do the integral. And I think right now the only thing that's really important is making sure that you guys understand the whole setup. Okay? So I'll leave it at that. Hopefully that made sense. So hopefully the problem set will be easy for you guys to do. And I'll just leave you guys to it. Take care.